Welcome to lecture 19 for Physics 220. Today we're going to be talking about Faraday's law. Now Faraday's law is actually some new physics. So this is not already contained in the Biot-Savart law. So it's distinct. All right, so last time we were talking about magnetic flux through a surface. So if you have some open surface, maybe some wire surrounds a region of space, and you have magnetic fields through there, we've learned how to calculate the flux through that surface. There's a perpendicular to the surface, and that would be the direction of dA, for example. Anyway, and we could calculate the flux that happens through this big surface here. Okay, now if that changes in time, then that causes a voltage around the edge of the surface. So if you come around looking at this path around the surface and you go all the way around, that gives you a voltage around it. So that is Faraday's law. Flux through a surface gives you a voltage around the edge. So this is a EMF, or voltage. Electromotive force. Okay, so here shows a bunch of pictures of what happens if you, for example, make a coil of wire. So that creates a perimeter of a surface, and now you wave a magnet nearby. Maybe you bring the north end in close, like in picture A, and then you pull it away. As you're pulling that away, you are decreasing the flux. And so that's means there's a time derivative. That's a function of time, and that gives you some kind of voltage around the edge, and that induces a current to flow, and you can see there's a needle there showing current in a certain direction. On the other hand, you could, depending which way you're going, so over here on A, you're bringing the magnet in, increasing it, that would make the current the other way. So decreasing or increasing flux, those are opposite signs on the derivative. They'll give you opposite voltages. Do the same thing with the south end of the magnet. Now if your magnet just sits still, it's stationary, then no current will flow. You really need this time derivative to cause a voltage, so things have to move. All right, so again, we're talking about a voltage. So volts, this E stands for volts. And in general, we're talking about this voltage. It's a voltage of an E field integrated around the edge of a circle. So we know that E field times the distance gives you voltage. And so we're talking about the voltage that would happen if you go all the way around the perimeter, a closed path of that E field dot the path you took, the dot the ds. That's the EMF that we're talking about. And that has to match this negative, the time derivative of the flux through the surface. I don't worry about the minus sign too much. So this is an open surface, B dot dA, whereas that's a closed path. That's the path that surrounds the surface that you calculate. Okay, that's Faraday's law. Let me give you a little example. You may in your house may have noticed, like in places like the bathroom or kitchen where there's running water, there are these plugs that have a little red button on them that they're called a GFI breaker. GFI breaker. And that stands for ground fault interrupt. So this is a safety thing. So it's different than the breaker in your breaker panel in your house. That one simply tests, do I have too much current flowing? And if so, I'm going to trip and turn that off. On the other hand, these little GFI breakers that are often built right into the plug in some area, and also on the outdoor of your house, what this does is test something else. It's not testing for how much current is flowing, although it has some threshold, but it doesn't take very much current to set it off. What it's testing is all the current that I'm sending out on one line, is it coming back where it's supposed to? So I'm coming out with current. Of course, it's a circuit, so you have to have a line coming back. It wants to know that what's sent out is coming back, because there's a third wire. Your ground wire is over here, and that's there for safety. So if something goes wrong, hopefully it sends the electricity into the ground wire instead of somewhere else. But the concern is that maybe the current gets to the ground through a person and they're getting shocked. And it doesn't take that much current to shock you pretty bad. Could be lethal even if you're hooked up long enough. So what this test does is says, I want to make sure that the same amount of current that goes out on this one wire is coming back on the wire it's supposed to. If it's not coming back on that wire, then it's probably coming back on the ground, and it could be going through a person on its way to ground. So here's how it tests it. It has the current going out and coming back, and these two wires go through they'll use an iron core. We've learned how the material can really enhance the amount of magnetic field. So this is supposed to have zero current through it when all is working well. In other words, when the same current is coming back on wire 1 as goes out on wire 2, then all is well. You have zero net current. And so that's Ampere's law in action right here. Ampere's law. That is, we'll do that integral around the circumference. So in that little iron donut, we go around that, and that's supposed to match the current enclosed, times E, or mu naught. There we go. So that's Ampere's law. Now, there's a secondary coil. So there's this little coil of wire around here. And so what this is doing is testing for magnetic flux through that coil. And so that one is Faraday's law. So if for some reason you get an imbalance of current, then you end up with a magnetic field and in the iron ring, and that's going through your coil. Now this is alternating current. So 60 times a second it's changing directions, and so if there's a different current going out as coming in, then you get a magnetic field in the ring that's oscillating at 60 hertz. And so it's changing in time. It's changing the flux through that secondary coil, the sensing coil. And so Faraday's law kicks on in and says, hey, there's a voltage coming out of this coil, and that will trip the breaker. So that's how those work. All right, let's look at a problem that we actually already knew how to do. Let's look on the left. We have a metal bar, and it's flying along here with velocity v to the right. Now, in the metal, we have charges that are mobile, and these charges, as they're flying through this magnetic field, and it's drawn here into the page, we've got these X's all over. So now you have a V cross B situation. So you have a force on the charges, which will be Q times V cross B. Now those are perpendicular. And so the magnitude of the force on those charges, that'll actually be the electrons, will be Q times VB, since those are perpendicular. Now that's going to cause a positive charge to build up at the top, up here, and negative charge to build up down here. And so these charges will set up an electric field. So more and more charges will pile up on the ends, except that too many of them there starts to create an electric field that stops it from happening. So there's going to be an electric field built up inside of this bar to exactly counteract that force. So the force electric would be Q times E, the electric field that results, and that's from the top toward the bottom. And that's going to counter the other one. So in other words, we have Fe magnitude equaling Q times E. All right, so finally, we can say that those are going to be in balance. Fb equaling Fe, so it's in equilibrium as that bar is flying along. And so we've got QVB equaling QE. We can cancel the Q's now, and we find out that the electric field equals V times B. Now, there's going to be a voltage there as a result. So our voltage, that's going to be the length of our bar times the electric field, and so length times V times B. All right, there is the voltage that we'd get between the ends. So this is voltage between ends. Good. Now let's redo this problem using Faraday's law. So we're going to revisit this. Faraday. So let's just say using Faraday's law. By the way, Michael Faraday lived in the early 1800s and figured this law out. He was a really brilliant scientist. He made a lot of contributions to chemistry through his life too. He figured this out empirically. He didn't know mathematics that well, and so the idea of a derivative was a little strange to him, but he still came to this conclusion and got it right. So here we go. According to Faraday's law, our EMF, or our voltage, will be this time derivative. Now you can put the minus on there, technically should be there, but that has to do with the direction of the current. We'll talk about that some more later. So I'll draw the minus sign and just say, don't worry about it. All right, so now what's our flux? Our flux is going to be the area, which it looks like X times L would be the area of that rectangle, which because the bar is moving, that's an increasing area, times the magnetic field. All right, so then using Faraday's law, we have our voltage around the loop. That would be causing current to flow through that resistor. That's going to be then time derivative. So we've got a constant L, constant B field, but X is changing. So I'll put the time derivative on that. Everything else can come out of the time derivative. And of course, a good name for dx dt would be velocity. So there we have it, B times L times B. There's our voltage according to Faraday's law, and that looks like what we concluded the other way. All right, now what's interesting, I'll get to that in a second. Here shows another example of something that you might think about using Faraday's law. So let's have a little loop of wire, and we're going to have it start outside of a region of the magnetic field and move with velocity v through that region. And so before it goes in there, nothing is happening. But as it enters the field, the flux went from 0 and then it goes up. Once it's in, you've got maximum flux, but it's steady. And then when you leave, your flux is decreasing back to 0 as this thing flies through at speed v. So it's these places where the derivative of that flux in time is non-zero. So here shows your EMF. You get an EMF in one direction as you enter, and then as you leave, you get an EMF the other direction. When you're in the magnetic field just flying along, the EMF is 0 because the flux is not changing. The derivative of a constant flux is 0. So that's the way to think about this. Okay, now I told you don't worry about the negative sign too much. So there's a law called Lenz's law, which its sole purpose is just to help you get the sign right, or the direction of the current right, when you're using Faraday's law. So here's Lenz's law. The induced EMF, or voltage, is always, or let's just say always tries to keep, let's say make current in a direction to keep the magnetic field the same. It doesn't like a change in magnetic field. All right, so let's see what I mean here. So in these pictures we have somebody holding a magnet and bringing it nearby. If they're moving the North Pole toward the wire, what you're doing is increasing the flux, or increasing the magnetic field to the left in this left picture. And so the current is going to want to flow in that loop in such a way that it will oppose that change. So it would make it in a direction that would produce a magnetic field from the current that would be to the right. And so that would resist that change. On the other hand, if you already have strong magnetic field in there and you're pulling the magnet away, then it would induce the current to flow the other way, because it's trying to keep that original magnetic field there. Okay, so that's Lenz's law. If you just keep that principle in mind, don't worry about the minus sign, and just look at the problem and think about, okay, which way is the current using my right hand rule going to want to flow, such that it will try to, if it's successful in flowing current, it would make a field that would help keep the field the same as it was to start with before you started moving things. All right, we better stop for a pause for a little joke. Why did the chicken cross the road? So these are answers supplied by famous physicists as to why this happens. Now, I think students in a physics class will especially appreciate this list. So here we go. Why did the chicken cross the road? From Newton, he says it was pushed onto the road by another chicken which went away from the road. Number 9, from Pascal, the chicken was pressured to cross the road. Number 8, another one from Newton, chickens at rest tend to stay at rest. Chickens in motion tend to cross the road. Number 7, Wolfgang Pauli, there already was a chicken on the other side of the road. Number 6, Newton, he said it was attracted to a chicken on the other side of the road. So Newton's had a lot of entries here. Number 5, Hawking, Stephen Hawking, he said the first seconds made the universe in such a way that chickens cross roads. Number 4, from Einstein, we might as well say that the road moved beneath the chicken. Number 3, Pierre de Fermat, famous for Fermat's last theorem. He says, I just don't have room here to give a full explanation. So he claimed to have proven his theorem, which was not proven until the 1990s and took over 200 pages. And he said that he could prove it, but he just didn't have room to write down and include the proof. So no one believes that. Number 2, Paul Erdos. This is a solid state reference. It was forced to do so by the chicken hole principle. And the number 1 reason that chickens cross the road is from Werner Heisenberg. We are not sure which side of the road the chicken was on, but it was moving very fast. All right, electromotive force. What are the units? I think we've had this question before. And the answer is volts. Of course, electromotive force and potential and volts are all synonyms for the same thing. We probably should just have one word, but everybody uses all three of those interchangeably, and the other ones sound wrong, but means volts. Lenz's law contains additional physics not present in Faraday's law, and that is false. This is part of Faraday's law. Its only purpose is just to help you get the sign right for Faraday's law. All right, Faraday's law applies to which of the following scenarios? Moving a magnet near a loop of wire causes an electric force around the loop. Moving a loop of wire near the magnet, so moving the loop instead of the magnet, causes an electric force around the loop. C, turning off an electromagnet near a loop of wire causes an electromotive force around the loop, or all of these scenarios, and the answer is D. So all of those work. Now we did an example where we had the bar moving through the magnetic field, so kind of like the middle case, and we were able to, using the force law for magnetic fields, come up with the right voltage around there. But we couldn't have used that law to do the other cases. It turns out Faraday's law applies to any of these situations. In fact, Einstein, in his first paper on relativity, he was very interested in these first two because it's really the relative motion between the magnet and the loop that matters, as opposed to one being stationary and the other one moving, or vice versa. So a conductor slides on a rails as in the presence of a magnetic field as shown. A resistor connects the rails. In which case does the current in the resistor flow up? And the answer is B. The reason is we can use Lenz's law. So we're decreasing the flux through here. So the magnetic field is into the page, and we're getting less into the page as that bar slides to the left. You have less flux, and so the current is going to want to try to keep that flux. And so, using the right-hand rule, I could point my thumb into the page in order to preserve flux into the page, and then when I curl my fingers around, it's going to make a current that goes up. Okay, so right-hand rule tells me that's the one. Okay, the diagram, and also Lenz's law. So this diagram depicts the possibility of current flowing in a wire as a result of moving the north end of a magnet away from a coil. So don't worry about these silver cylinders. That's just maybe some plastic there just holding the wire in place. So we are moving the north end away from the coil, and then we're looking here and deciding which picture is correct. There's some indications of direction of current, and the middle one has no current, and so you have to look at that and decide which one is the correct picture. And the answer is C. Okay, so the way to think about this is you have magnetic fields coming out of the north end of the magnet, so you have a lot of magnetic flux coming in from the right there, and so as I pull that away, the coil is going to want to have current flow in such a way that as to preserve magnetic field going to the left. Okay, so if my current is going like this, I can wrap my fingers around the solenoid in the direction of the current, grab the solenoid, and then my thumb would point in the direction of the magnetic field that current would make. And so you want a current such that it would make magnetic field to the left, and then that will try to, as you're pulling that magnet away, it's going to try to keep some of the same magnetic field there. So that's the direction of the current by Lenz's law and the right-hand rule. All right, current is induced in a wire as a result of changing the magnetic field. Okay, so maybe that's an electromagnet there, we're turning it on and off. And so we have some current in the wire. Looks like this current that's induced is shown there. So we have the current going around this way, around like that, and out. And so we wonder if the magnetic field is decreasing in time, staying the same, or increasing. And the answer is C, increasing. If I use the right-hand rule, I can figure out that my coil is making a magnetic field that's down, opposing the magnetic field. So it would want to do that if it was, by Lenz's law, it's trying to keep the field the same. So if the field's increasing, it would make a field that opposes. Okay, see you in the homework help.